Hello class, welcome to our Combinatorics lecture for Wednesday, April 22nd. Well, this is kind of a red letter day because this is the last lecture of new material for the course. And so today we're going to continue talking about solving linear recurrence relations. But today we're going to look at the case where the recurrence relation is non-homogeneous. So I'll remind you what that definition means here in just a moment. So we will, I will tape a video for Monday, April 27th, but that is just going to be me looking at the solutions to the questions on sample test number 3, which has been posted since this weekend. So I already sent an announcement about the posting of sample test number 3, and I should have by this weekend the written answers. I'm not sure how complete my solutions will be, but the written answers for the questions on sample test number 3. But then again on Monday, I will on Monday's video will not be new material. It will just be going over some of the key problems from that sample test. So that will sort of function as a review for your test number 3, which will be posted on Monday, April 27th as well, and then that will be due back on Wednesday, April 29th, right? Okay. And so you do have also posted homework 7. But remember, that is an optional homework, right? You can, that's just to give you practice for more problems, practice for test number 3. You can submit that homework when you submit the test, but test number 3, but you don't have to submit that homework. So if you do submit it, I'll grade it. That might improve your homework score if you feel like you need improvement in your homework score, but if your homework score is fine, then you do not have to submit homework number 7. That's just merely for your benefit, your practice benefit, right, for test number 3. Then the final exam will be the following Monday, but many of you can be exempt from the final exam if you are happy with your midterm test score average. Then you can use that as your final exam score, and so then you will not have to sit for the final exam. But if you think that you want to improve your course average, then you can do that through taking the final exam, right? So that's sort of the sequence of events between now and the end of the semester, right? The big upcoming event is taking that test on Monday, April 27th. Okay, so I hope everyone is doing great and is safe, and maybe a little stir crazy if you're trapped in your home or in your apartment like me. But otherwise, I hope everyone is doing fine. This material on recurrence relations is not really covered very well in the text, so that's why I did not pick homework problems for homework number 7 from the text, and the sample test questions are not from the text. I think the way the book talked about recurrence relations is a little bit more complicated than it needs to be. So looking at the notes and looking at the videos is really going to be helpful in understanding how to do the questions on the sample test and the questions on the homework, and then the questions on test number 3, at least as it relates to recurrence relations, setting up recurrence relations, and then solving recurrence relations. Of course, if you're watching this video, then I guess you already intend to watch the videos. So I may be preaching to the choir here, but anyway, if you're wondering why am I not using the textbook so much for this last material, that's because I think the textbook's explanation of it is a little bit unnecessarily difficult for what we're trying to accomplish. Okay, so I think I've said almost everything that I need to say, but remember, you can always join me if you've got questions. You can always join me for my Zoom office hours correct. So I will have office hours on Wednesday, April 22nd. After this video is posted at 3 p.m. right, and then on Thursday at 9 a.m. and then on Friday at 10 a.m. and then you can also catch me next week at those same times, right? You can ask me questions, before you have to submit test number 3, right? Or before we take the final exam on Monday, May the 4th. Okay. All right. So let's go ahead and dive into the notes so we can finish this in a reasonable amount of time today, so I don't run over and our allotted time. Last time we looked at this. And this is going to be very useful on your test, right? And this is a pretty easy process. So this is something that you can learn and I think get these questions easily. This is the process of solving certain types of recurrence relations, in particular linear second order recurrence relations that are homogeneous. So that's a lot of terminology, right, that we went over last time, but let me remind you of that. So this is in the notes from last time, and this is sort of the body of the theorem that was sort of the key theorem, which sort of describes how to solve these linear second-order homogeneous recurrence relations. And it's easy, actually, probably an easier theorem to apply than it is to actually review here, but let me remind you of the key points. So suppose we have a linear second order homogeneous recurrence relation. So that's going to be a recurrence relation that looks like this, okay? And so remember, what makes it homogeneous is that, again, when you take the recursive terms, so these are the recursive terms, right, in the recurrence relation. When you take those and pull them to the left-hand side of the recurrence relation, then of course you're going to get something on the right-hand side as well. But if that turns out to be 0 on the right-hand side of the equation, which happens in this recurrence relation, right, when I move these two recursive terms to the left-hand side of the equation to join this other recursive term, s sub n, well, you get s sub n minus a, s sub n minus 1 minus b, s sub n minus 2 equals 0. And because now the right-hand side of this equation is 0, that's what makes the recurrence relation homogeneous. So if this right-hand side does not turn out to be 0, and that's going to happen in recurrence relations, sometimes this right-hand side will not be 0, then if it's not 0, that's called a non-homogeneous recurrence relation. All right. Now, all right, so that's the difference between homogeneous and non-homogeneous. Now, in the process of finding the solution to the recurrence relation, remember, we're going to write down what's called the characteristic equation for the recurrence relation, and we get that by taking the coefficients, right, from this equation and converting them to a polynomial equation. So this first coefficient is 1, so I would write down 1x squared minus a times x minus b is equal to 0, okay? By the way, the characteristic equation is always set equal to 0. I don't get the 0 from the right-hand side of this equation. You just take these coefficients from the recursive terms, right, and you turn them into a polynomial, and then you set that equal to 0. That's called the characteristic equation for the recurrence relation. And whatever the degree of that characteristic equation is, that's called the order of the recurrence relation. So this is a second order recurrence relation because this is degree 2. This theorem is stated in terms of second order recurrence relations, but this theorem works for other order recurrence relations as well. It's not restricted to just second order. Okay, so in the notes today we'll look at using this same theorem, but we'll apply it to a first order recurrence relation, homogeneous recurrence relation. Now, the linear part comes from the fact that when you, again, look at the terms of your, the recursive terms of your recurrence relation, S sub n, in this case S sub n minus 1, and then S sub n minus 2. Notice those are all raised to the first power, right? And since these are all raised to the first power, then since these recursive terms are all raised to the first power, that means that this recurrence relation is linear. All right. So if we have this particular type of recurrence relation, in this case linear, homogeneous, second order, how do we solve it? What's the solution? And this very nice theorem says, okay, take your characteristic equation. That's in this case a quadratic equation, right? Because it's degree 2. Find the solutions for that quadratic equation. You can always do that either by factoring or using the quadratic formula, right? So find the solutions to the characteristic equation, and once you found the solutions to the characteristic equation, then it's going to be powers of those solutions that will give you the solution to the recurrence relation. So you take an arbitrary constant C1 times the first solution to the recurrence, to the characteristic equation, raised to the nth power, plus, again, a second arbitrary constant times the second root of the characteristic equation, the second solution of the characteristic equation raised to the nth power. That is the guaranteed non-recursive solution to the original recurrence relation. Now, if it so happens that your characteristic equation only has one solution to it, okay, it's second order, but it only, so it's a quadratic characteristic equation, but if it only has one solution, because quadratic equations can have only one solution, right, sometimes, then here's how you form the solution to the recurrence relation, right? Notice that it's very much like forming the solution when you have two roots, except to distinguish this second term from this first term, since this r is the same, you only have one solution to the characteristic equation, right? Then you throw in, to distinguish these two terms, you throw in this extra factor of n in the second term. And that's how you get your solution to the recurrence relation. And again, now these constants C1 and C2, how do you find them? They depend on the initial conditions that you're given for the recurrence relation, right? So usually when you're given a recurrence relation, you'll be given values for small instances of the recurrence, and so you can use those to, by substitution, you can use those to figure out what these constants C1 and C2 are. So we saw examples of that in the notes for Monday, right? So if you haven't looked at the lecture for Monday, April 20th, take a look at that, and it will show you examples of using this theorem. Now, so we're not going to go back over this theorem today. We will use it again today. Today we're solving non-homogeneous recurrence relations. So we will use the theorem again, however, okay, even though we're solving non-homogeneous recurrence relations, we'll still have opportunity to use this theorem, although it specifically applies to homogeneous recurrence relations. So I was going to entertain you with a proof of the theorem and show you why these expressions that I've given are solutions to the recurrence relation, but I don't think that, I've rethought that. I think that in this context of just watching me talk on tape here instead of face-to-face, I don't think a proof of this theorem is going to be very entertaining, so I'm going to forego that. However, the proof is in the notes, so if you look through the notes for Monday, April 20th, there is an outline of the proof. Okay, so you can read there. It's not a difficult proof why this particular theorem is correct. Okay. Now we're going to use this again today in solving, as I mentioned, in solving non-homogeneous recurrence relations. And so, so we will have an opportunity to practice this a little bit. And again, and I do want to remind you, this same theorem, although it's stated for second order linear homogeneous recurrence relations, it works for other orders as well. So it would work for first order linear homogeneous recurrence relations, an example of which we're going to see today, or it would also work for third order or fourth order or higher order homogeneous linear recurrence relations. We're not going to see any examples like that, but the theorem does apply for those higher orders as well. So this really is a powerful theorem, except it only works for homogeneous recurrence relations. So today we're going to take up the issue of, well, what if when I set my when I pull all my recursive terms in my recurrence relations, if I pull them to the left-hand side, what if the right-hand side does not turn out to be 0? Okay, how can I solve recurrence relations like that? Because that sometimes is going to happen in recurrence relations. In fact, we've already seen examples of that in earlier notes when we were setting up recurrence relations for counting certain sets. All right, so okay. So, well, let's just dive into this, right? So, what's written here in the notes are kind of repeating what I just said there a moment ago. Here's an example of a second-order linear homogeneous recurrence relation, right? Because if you take the recursive terms and pull them to the left-hand side with S sub n, you get this equation, right? S sub n, so our original recurrence relation is S sub n is equal to 2 S sub n minus 1 plus 3 S sub n minus 2. But when you take these two terms and, again, move them back over to the left-hand side, these are recursive terms because they involve S sub n minus 1 and S sub n minus 2. If you move those back to the left-hand side of this equation, well, you get easy to see, right? S sub n minus 2 sub S sub n minus 1 minus 3 sub S sub n minus 2 equals 0. And notice the right-hand side of this equation is 0, so this is a homogeneous recurrence relation. It's also linear, because the recurrence terms, right, the recursive terms are all raised to the first power, so it's linear, and it also happens to be second order. All right, so we know how to solve, make a long story short here, we know how to solve this recurrence relation. That is the point of the theorem that I was just reviewing a moment ago. Okay, so we know the steps for doing this, and they're pretty straightforward and well-defined. Now, however, let's slightly alter the recurrence relation. Okay, so I'm going to change it a little bit just to make it non-homogeneous. All right, and then we're going to talk about what happens in that case. So what I'm going to do is add on here to the same recurrence relation, I'm going to add on one extra term. But notice this is not a recursive term. It doesn't involve S sub n minus 1 or S sub n minus 2 or S sub n minus 3, right? This is not a recursive term. It does involve the variable n, but it's not recursive, all right? So when you take this recurrence relation, very similar to this one, right, and pull the recursive terms to the left-hand side, then, well, you get this equation, right? Okay, S sub n minus 2 sub S sub n minus 1 minus 3 sub S sub n minus 2 equal n. That is not 0 on the right-hand side anymore, right? Okay, not 0. So that means that this recurrence relation now is non-homogeneous, all right? This is called non-homogeneous. And so what we want to talk about today is how we can solve this recurrence relation. Now, the method that I'm going to show you here is not going to be a very satisfying method, all right? We are going to be able to solve this recurrence relation, but the method that I'm going to show you is not very satisfying because it's not very general. In general, you cannot solve non-homogeneous recurrence relations. There is no one method that will allow you to solve non-homogeneous recurrence relations. So that in general is a difficult problem. However, we do have some scattershot methods that you can use to solve non-homogeneous recurrence relations, and they work sometimes and sometimes they don't work, okay, because there's not a single method that will work in every case. So I'm going to show you a method that applies in this recurrence relation and sometimes applies in other non-homogeneous recurrence relations, and but don't get too excited. It's not really that powerful, okay, because there is just no general method for solving non-homogeneous recurrence relations. So this is sort of the best we can do, given the short amount of time that we have to talk about non-homogeneous recurrence relations. And it will work well for the problems that I gave you on the sample test and the problems on the test, but don't expect this to solve every non-homogeneous recurrence relation, because that's not possible. All right, so let me show you now how this sort of, again, this is sort of an improvised scattershot method that works in this case, and it works in certain other cases, but if you try it in other problems, it doesn't get you very far, okay? But it works well here, and it's going to work well in the next example too. All right, so here's what we're going to do. So here is that non-homogeneous recurrence relation. I do have some initial conditions, and we can use these initial conditions later, but we don't need to have them immediately, okay? But there are the initial conditions. S sub 0, as it turns out, in this example, is 1, and S sub 1 is also 1, all right? And in general, S sub n is 2S sub n minus 1 plus 3S sub n minus 2 plus n. So, for example, just to do one little quick calculation here, so I'm prone to making errors when I do these calculations, right? We know that S sub 2 would be 2 times S sub 1, right? Because 2 minus 1 is 1, right? Plus 3 times S sub 0, right? Okay, because 2 minus 2 is 0, right? And then plus, however, you're going to throw in the value of n, the index here. So that would be plus 2, right? So let's see, what is S sub 2 then? S sub 1 is what? 1. So you have 2 times 1 plus 3 times S sub 0 is also 1, according to my initial condition here, plus 2, right? So what does that add up to? 2 plus 3 plus 2 is what? Is that 7? All right, so we know that S sub 2 is 7, and then, of course, now we know S sub 2, we could go on and compute S sub 3, right, and so on and so forth. So, of course, it's easy to see how the recurrence relation works, right? But now we want to take that that recursive method for computing S sub whatever, right? And then we want to see if we can write down a non-recursive formula for computing S. Okay. All right, so here's what I'm going to do. It kind of starts off the same as before. We're going to take the recursive terms and pull them to the left-hand side of my recurrence equation, right? So I get S sub n minus 2 S sub n minus 1 minus 3 S sub n minus 2 equals n. And so we immediately notice, oh, this is not a homogeneous recurrence relation, right? Because this does not turn out to be 0. Okay. All right. So so the theorem from the last notes does not immediately apply here, right? To help me solve this recurrence relation. But here's the trick that I'm going to use that works nicely on this recurrence relation and works nicely on other recurrence relations sometimes, right? Non-homogeneous recurrence relation, but it doesn't work perfectly in general. All right. So notice this this non-homogeneous term here over on the right-hand side. That is a function of the variable n, right? Because n is a variable, right? It changes every time the subscript changes. What sort of function of n is that? That is a linear function of n because, right, this is n raised to the first power, right? So, you know, when you have a variable and it's raised to the first power in an expression, that's going to be a linear expression. So here we have a linear expression or a linear function, however you want to call it, of the variable n. That's this non-homogeneous term on the right-hand side of the recurrence relation. Now, functions of the linear functions of the variable n, what do they look like? Okay, this is an example of a linear function of the variable n, right? But in general, what do linear functions of the variable n look like? Well, remember your knowledge about straight lines, right? Linear functions have this form, correct? You're going to have a constant times the variable plus a second constant. this constant you usually call the slope, right? And this constant you know is the y-intercept, correct? If you were to make a graph of this linear function. But in general, this is what linear functions with variable n is the variable here, a and b are constants, n is the variable in this expression. And so since n is a linear function of itself, right, okay, then we're going to suppose, we're going to make an assumption here. It's kind of out of the blue, but we're going to make an assumption here, and sometimes this assumption works and sometimes it doesn't. We're going to assume that we have a solution to the recurrence relation of this form, a linear function of n. So I'm going to suppose, and we'll see how far we get with this assumption, but I'm going to suppose that S sub n is equal to a linear function of n, okay? So a times n plus b. And what triggered that? It's just this observation that the non-homogeneous term in my recurrence relation was a function of n. All right. Now, what I have to figure out here is what could I use for a and what could I use for b? So what's the slope here and what's this y-intercept, so that this assumed solution actually turns out to be a genuine solution, right? Okay, and maybe there's nothing I can choose for a and b that will make this into a solution for the recurrence relation, and if that's the case, then this method didn't get me anywhere, right? And sometimes this method that I'm showing you doesn't get you anywhere, all right? But let's see what happens in this case. So I'm going to assume I have a solution to the recurrence relation. This is not a recursive, right, formula, correct? So I'm going to assume I have a non-recursive solution to the recurrence relation that looks like this, a times n plus b. All right, now, what's the implication of that? All right, well, let's see. If S sub n is a times n plus b, right, then let's plug that in to my recurrence formula, right? So S sub n, right, is a times n plus b. See, that's what I plugged in for S sub n. And that is supposed to be equal to, according to the recurrence relation, right, that's supposed to be 2 times S sub n minus 1 plus 3 times S sub n minus 2. Well, what would S sub n minus 1 be according to this formula? Notice that would be a times n minus 1 plus b, right? And what would S sub n minus 2 be according to this formula? Well, S sub n minus 2 would be a times n minus 2, right, plus b. So in this recurrence equation, where I see S sub n minus 1, I'm going to plug in a times n minus 1 plus b. And where I see S sub n minus 2, I'm going to plug in a times n minus 2 plus b, right? So I get 2 times, that's a times n minus 1 plus b, plus 3 times, well, a times n minus 2 plus b, right? And then don't forget the plus n that has to be added on to the end, right? So again, I'm just making this bold assumption that I have a solution to the recurrence relation that looks like this, and now I'm kind of testing out that assumption, right? So I'm plugging this formula into the recursive version of the recurrence relation, right, to see if I can make this formula a n plus b work. All right, well, now let's do just some algebraic simplification here. So I multiply here by the 2 and the a, and I get 2an minus 2a plus 2b plus, and then here multiplying out 3an minus 6a plus, oops, is that supposed to be plus? Yeah, plus 3b, right? Okay, and then plus n. So I'm just simplifying all of these brackets and parentheses, right, by multiplying through. And now I'm going to add some like terms together and rearrange my terms a little bit. So I'm adding like terms and rearranging terms, and I get 5an plus n, that n is this n, and the 5an comes from 2an plus 3an, right? So that's 5an plus n, and then plus, when you add your b terms together, you get 5b, and when you add these a terms together, you get minus 8a. So I have 5an plus n plus 5b minus 8a on the right-hand side of this equation. Now remember, on the left-hand side, I still have an plus b, because that's what s sub n is equal to. All right, now, how many n's do you have on the right-hand side? Well, these two terms contain n, right? So I'm going to factor the n out of these two terms, and I get 5a plus 1 times n. So 5a plus 1 times n is just the same as these two terms, okay? And then, of course, at the end here, I've got plus 5b minus 8a, right? Right there. Now, here's the observation I'm going to make. Look, these two sides of this equation are equal, right? So on the right-hand side, you have 5a plus 1 times n, but on the left-hand side, you have a times n. So what that means is that a has to be the same as 5a plus 1, correct? In other words, I'm going to equate these coefficients of n on the left and the right-hand side. And notice that this is a constant because it doesn't involve, all of this is a constant, right? Because it doesn't involve n. And so on the right-hand side, you have this constant 5b minus 8a, right? But on the right-hand side, you have just this constant a. So, I'm sorry, just this constant b. So what that tells me is that b has to be the same as 5b minus 8a. See, this is a constant because it doesn't involve n. This is a constant because it doesn't involve n. If the left-hand side and the right-hand side are equal, that means b has to be the same as 5b minus 8a. So I'm going to write down those two equations. I know this has to be true. A has to be 5a plus 1, and b has to be 5b minus 8a. But now, these two, see, look, you've got two equations, and they only have two unknowns in them, right? A and b. So you can solve these two equations for the two unknowns, a and b, right? Just using some elementary algebra. Actually, it's really easy in this case, because the first equation, I think, already tells you that if you solve that, see, that equation doesn't have b in it, right? So you can solve it immediately for a. So you get a, I think, is minus 1/4 if you solve that equation for a. And then if you plug that into the second equation now for a and solve for b, I think you get b equals minus 1/2. You can try that and see if that's going to work. Let me write my class in here. All right, so there I said it, right? A is minus 1/4 and b is minus 1/2. So that means, remember, our assumed solution to the recurrence relation was an plus b. But if a is minus 1/4 and b is minus 1/2, then there it is. There is a solution to the recurrence relation. See, notice that's non-recursive, right? On the right-hand side of this equation, you don't have s again, right? You don't have s sub n minus 1 or s sub n minus 2, right? So this is a non-recursive solution to the recurrence relation. So see, that worked out quite nicely, right? We found a solution to the recurrence relation. Now, there are actually other solutions to this recurrence relation. Let me show you how you can get all of the solutions to the recurrence relation. Okay, so there's another step here. So this is one solution to the recurrence relation, but I claim we can get all solutions to the recurrence relation by doing the following. So hang on to this. We want to keep that solution, minus 1/4 n minus 1/2. But now let's take the recurrence relation, this is the original recurrence relation, and let's make it homogeneous. Remember, it was non-homogeneous to start with. So we're going to make it homogeneous by dropping the n. Remember here in the non-homogeneous recurrence relation, we had plus n. That's what we were looking at a moment ago. Now I'm going to drop that and just write down the homogeneous version of the same recurrence relation just by dropping the n. Now we're going to find the solutions to this homogeneous recurrence relation. Okay, so this is kind of step 2 here, right? Turn the non-homogeneous recurrence relation into a homogeneous recurrence relation by dropping the non-homogeneous term, and then find the solutions to that homogeneous recurrence relation. That's what the theorem from the previous notes can help us do, right? So what did the theorem from the previous note say? It says, look at the characteristic equation. What's the characteristic equation here? Well, this is it. It turns out to be x squared minus 2x minus 3 equals 0. Find the solutions to that characteristic equation. Well, we can find those by factoring in this case, so we don't have to use the quadratic formula. So the solutions are x equals 3 and minus 1. We can find those by factoring. So what do we know the solutions to the homogeneous recurrence relation are? It would be s sub n is equal to some constant times, take the first root, this is 3, raise it to the nth power, plus a second constant times, take the second root, minus 1, and raise it to the nth power. Oh, so look, now you've got the following here. You found this solution. This is the solution to the homogeneous. This is the solution to the non-homogeneous recurrence relation, right? That's the solution to the original recurrence relation. Now you find this is the solution to the homogeneous version of the same recurrence relation, and now you combine these two solutions. And when you combine these two solutions, what you end up, combine by addition, these two solutions, and when you do that, what you've got are what you end up with are all possible solutions to the original non-homogeneous recurrence relation. That's it. That's all possible solutions to that original non-homogeneous recurrence relation. Remember, that was s sub n equals, oh shoot, I forgot here, what was it? 2 s sub n minus 1 plus 3 s sub n minus 2 plus n. Every solution to this recurrence relation looks like this. Okay. Interesting. I'm not going to verify that now, but you can try verifying that, okay, by actually plugging in to, this is an N, by the way, by actually plugging this non-recursive formula. Try using that in this recurrence relation, and you'll see indeed that this is going to be a solution to this non-homogeneous recurrence relation. By the way, now you're going to ask me, what is C1 and what is C2? These are arbitrary constants. You find those by, remember, using your initial conditions. So remember, your initial conditions were s sub 0 equals 1 and s sub 1 equals 1. So by using s sub 0 equal 1 and s sub 1 equal 1, you can, like in the previous notes, you can determine what these two constants would have to be. Okay, I'm not going to go through that process. We practiced that last time in the prior notes. Okay, so use exactly the same process. All right, so that's the idea for solving non-homogeneous. So it's kind of a two-step process there, right? But again, it's not a foolproof process. So in some non-homogeneous recurrence relations, this is going to work well, but in others, it's going to fall flat. Let's try another example. We need to see one other example. All right, so there's written down what I just said. Use s sub 0 equal 1 and s sub 1 equal 1 to find what those constants C1 and C2 are. All right, so let's try this process again for a second example here. All right, so here our recurrence relation is s sub n is equal to minus s sub n minus 1 plus, so this is a recursive term, and then plus you've got these other terms here in your recurrence relation that are not recursive. Okay, so in this case, n squared plus 1. So this is non-homogeneous because when you take the recursive term and pull it to the left-hand side, you get s sub n plus s sub n minus 1 is equal to n squared plus 1. Unfortunately, that n squared plus 1 is not 0, right? Okay, so the recursive terms are not equal to 0. So that means that this is not homogeneous, Okay. All right, by the way, this is a first order recurrence relation, not second order. Its characteristic equation, by the way, is x plus 1 equal 0, which is, that's first degree, right? So this is a first order recurrence relation. All right, so how do we go about solving this non-homogeneous recurrence relation? Well, I mentioned, right, take a look at the non-recursive terms. N squared plus 1, right? Okay, so what sort of function is that with respect to n? That is a quadratic function, right? That is second degree function because you have n squared. What do second degree functions look like in general? Those are quadratic functions, by the way. So what do second degree functions look like? In general, they look like some coefficient times n squared, right? In this case, the coefficient is 1 times n squared. But some coefficient times n squared plus, you may also have some coefficient times n to the first power. Here, you don't have n to the first power, so that coefficient is 0. Right, and then you have plus a constant. So you have the famous expression for the famous formula for general formula for quadratic expression, right? N squared plus bn plus c. So what we're going to assume here is that we have a solution to the non-homogeneous recurrence relation that looks like this. Okay, again, looks like a general quadratic function. An squared plus bn plus c. And what we'd like to do now is to pick out the a, b, and c so that we do have a solution. All right, so let's see if we can do that. All right, so again, I'm supposing s sub n is an squared plus bn plus c. But according to the recurrence relation, so this is my assumption, right? This is what we're assuming. But we're not assuming this. This is what we're told. We know that s sub n is minus s sub n minus 1 plus n squared plus 1, right? So an squared plus bn plus c has to be minus s sub n minus 1 plus n squared plus 1. But what is minus s sub n minus 1? Well, if s sub n is an squared plus bn plus c, then s sub n minus 1 is going to be a times n minus 1 squared plus b times n minus 1 plus c, right? Okay, just plug n minus 1 in for n in this formula. But don't forget now, so s sub n is an squared, an minus 1 squared plus bn minus 1 plus c. But because we have this minus sign in front, that's going to change all these signs to negative. So all of this is minus s sub n minus 1. But don't forget now we have the n squared plus 1 added on to the end. All right, so again, what's happening here? I'm assuming that I have a solution that looks like this, an squared plus bn plus c. That's just an assumption. I don't know if that's true. But according to the recurrence relation, s sub n also has to be this. So, well, let's see what all that means. So look now, okay? I'm going to do a little bit of algebra on this line, okay? So I'm going to expand this product n minus 1 squared. I'm going to multiply by minus a. I'm going to multiply minus b into the n minus 1, right? Okay, so expand all of that. You come up with this, all right? And now let's sort of gather like terms together, right? So I have how many n squareds? I have a minus a n squared, right, and a positive n squared here. So that means altogether I have minus a plus 1 times n squared. How many n terms do I have? I have a 2an and a minus bn, right? So that means altogether I have minus b plus 2a times n. And then all the other terms are just constant. So the minus a, the plus b, the minus c, and the plus 1, these are all just constants because they don't involve the variable n. But remember, what's all this equal to? All this is supposed to be equal to this, right? A times n squared plus b times n plus c. So what you get now are three equations. They're pretty easy to see, right? If you have n squared here and n squared here, that means minus a plus 1, right, has to be the same as a. So I wrote that down as an equation. Minus a plus 1 is a. What about minus b plus 2a? That has to be b, right? So minus b plus 2a has to be b. And then finally, all of this has to be equal to c, right? So we get c equal to minus a plus b minus c plus 1. And now you've got three equations to solve with three unknowns, right? So you have a linear algebra problem here, right? Want to solve three equations with three unknowns. The first one is really easy to solve, though, because this equation only has one variable in it, a. So that first equation you can solve for a, and you get a equals 1/2. And then you can plug a equal 1/2 into the second equation and solve for b. So you end up with b equals 1/2. And then you can plug 1/2 and 1/2 for a and b into the third equation and solve for c. And when you do that, you end up getting c is also equal to 1/2. So there we've got it, right? We have coefficients a, b, and c that we know are going to make this formula a solution to the recurrence relation. So that would be what? S sub n is a is 1/2, so you have 1/2 n squared plus b is also 1/2, so plus 1/2 n plus c is also 1/2. So there it is. There is a solution to the non-homogeneous recurrence relation. That's one solution, though, okay, to the non-homogeneous recurrence relation. Now, how do we get all possible solutions to the non-homogeneous recurrence relation? All right, so go back to the original recurrence relation. Well, let's see if we can find it. Where is it? Way up here, right? And drop the non-homogeneous term, which was, in this case, there are two terms. So drop the non-homogeneous part of this recurrence relation, the n squared plus 1. So cut that out and turn that in. So turn this recurrence relation into a homogeneous recurrence relation. When you do that, you get this homogeneous recurrence relation, which I said, this recurrence relation is the same as this recurrence relation, right, which is homogeneous because the right-hand side is 0. This has characteristic equation x plus 1 equals 0. And, of course, the solution to that characteristic equation is x equals minus 1. So now from our previous theorem, from the previous notes, right, we know then that we have a solution to this homogeneous recurrence relation. It would just be S sub n is equal to, again, the solution to the recurrence relation raised to the nth power, and then times some arbitrary constant. Notice you only have one, right, since this is a first degree characteristic equation, you only have one solution, and so you only have to write one term in your recurrence relation solution, C1 times minus 1 to the nth power. So now that you've got this solution to the homogeneous version of our recurrence relation, what's all solutions to our original problem? Well, you take this solution and then add on that this solution that we found here. Just combine these two. and that gives you all solutions to the original non-homogeneous recurrence relation. That's it. And again, how do you find this constant? C1, you have to use the initial conditions if you're given any. I don't know if we were given any initial conditions in this problem, though, so we don't have to really try to bother and figure out what C1 is equal to. Okay, all right, so wow, there's how we solve at least one method that sometimes works, right, for solving non-homogeneous recurrence relations. Let me pause here for a moment, and then I'll come back in just a second. Okay, well, we're back here. So remember, so I already described at the beginning of the lecture right today, sort of the sequence of events through the end of the semester. So on Monday, again, I will post a video, but the video on Monday is not new material. What we just looked at was our last example for the semester. That's kind of sad, right? But that's our last example for the semester, and so on Monday, again, we'll just look at problems from sample test number 3, right? So we'll probably see another problem like this one on Monday because there are non-homogeneous recurrence relations on the sample test to solve, and you will solve them using the technique there that I just showed you. Okay, all right, so we're going to go over the sample test on Monday, and then you'll be all ready to take the test on Monday, I think, right? The test on Monday, remember, so you can see this from the sample test, but the test will cover inclusion, exclusion, derangements, which is just an application of inclusion, exclusion, and then recurrence relations, setting up recurrence relations and solving recurrence relations, right? Okay. All right, so have a good weekend, and prepare well for the test on Monday, and I will see you on Monday, unless you log on to my Zoom office hours, right, and I see you before then, okay? All right, so take care, as usual. Stay safe, right? Wash your hands, wear your mask in around crowds, right, okay? Practice good social distancing techniques, right, okay? The statistics for Harris County are quite encouraging. At least through today, the number of new cases has been falling pretty rapidly, actually. And so I think if you again follow these simple practices, social distancing practices, right, we will get through this pretty soon, actually. All safe. All right. So see you guys later. Bye.